because of a climate hazard. And so I think my objective here and coming to the conference more broadly is to really see how we can connect with those of you, particularly on the modeling side, to understand. By the way, is it okay that I don't use the mic? Yeah.
Can we have you use one of those microphones?
Yeah, I think there's some people on Zoom, so.
Okay, so why we're here, we want to connect with those of you on the modeling side to really see how our micro level data could maybe inform the parameters of modeling, or really to make that behavioral link once we have a readout from a model to understand what does that mean in terms of people's behavior. So any ideas, and if anyone wants to use the data that I'll share, we have, by the end of the year, we'll have more than 6,000 surveys. We're happy to do that because there's no way we can exploit all of it. So, so this year we've gotten support from the EU through a grant administered by ICMPD to carry out research on mobility linked to climate hazards. So for those of you who are familiar with EU funding, there was an MMD grant facility that was awarded to 8 projects in sub-Saharan Africa. Ours is the only one on climate mobility, and we're working with the University of Addis Ababa, but we're responsible for the data collection and analysis side. And through this project, we've got 4 main countries of focus: Somalia, Kenya, South Sudan, and Burundi. We're carrying out about 1,000 surveys in each country. Burundi and South Sudan will focus on internal mobility, whereas Kenya and Somalia will focus on international movements. But I also want to say we've got a few extra surveys in Djibouti, Somalia, and Kenya. This is because MMC has been carrying out data collection on climate mobility for a few years now. We had a major drought crisis, the largest to date in history in the Horn of Africa, where we had 3 successive failed rainy seasons and massive amounts of displacement, millions of people, and exhibiting very different migration patterns. And that was succeeded by some of the worst flooding that we've seen across the region. So we've been carrying out data collection on this issue since 2022. And how do we do that? So we use a standardized tool, not just on climate mobility, but in general. So if you're familiar with the work of IOM's displacement tracking matrix, the Mixed Migration Center has a similar tool called 4MI that's less concerned with measuring the total size of populations and more concerned with understanding the 360 degree of people's movements. So what their decision making is like, their aspirations, the routes they've taken, their interactions with smugglers, their onward movement decision making, the abuses that they've experienced along the way. So when the drought crisis broke out, we developed a climate mobility module to really understand how the environment was playing a role. And we learned that by introducing some direct prompting questions, we could really isolate how the environment was factoring into people's decision making. Because up until now, it's been a bit elusive because it's a more fundamental factor impacting more proximate drivers like economic livelihoods or factors related to conflict. So the unique thing about our data is it is a survey administered to migrants, including refugees, by migrants, including refugees. So they're not existing beneficiaries of humanitarian programming. I usually say that because MMC's legal entity is the Danish Refugee Council. So we are a humanitarian INGO, which means we have access to really difficult to reach locations in places like Somalia and in South Sudan. So we have this survey tool that we implement, but it's not tied to any existing humanitarian programming. And it's for adults. And we interview people who've been in a country for less than 2 years. I think that's the only other key sampling information to know here, in an effort to capture people who are actively on the move and not these more permanently settled migrant or refugee populations that you often see. So we can talk a little bit about what the tool looks like, maybe with the Q&A, but you'll see the climate mobility module includes questions that help isolate how climate factors interact with other drivers of movement, what types of climate disasters or events did people encounter, what were the impacts of the hazard on their household, triggers versus more fundamental drivers of movement, whether they were exposed to any kind of early warning system, what adaptations did they try, who stayed behind and why, just to name a few. So I won't spend too much time on the sample. 5 minutes are already gone, but I'm just going to zoom in on data that we've collected just in the last few months from Kenya and Somalia. And you can see that the gender balance is quite similar across the two groups. Where we see the biggest difference is in respect to age, family makeup, and nationality. And I think here's where I want to highlight the fact that there are things that we learned about mobility linked to climate change only when we started working with standardized data across multiple countries and putting these things in a comparative perspective. And what do I mean by that? I mean, the biggest thing that we've learned is that climate mobility outcomes are very much shaped by pre-existing migration patterns and norms in those locations. So in a country like Kenya, we see climate mobility patterns really echo the country's refugee movements. So many more families moving to Kenya, and you'll see later on in the presentation, more interaction effects with conflict, more decisions around permanent versus temporary moves. And so you see an older demographic and more people traveling, something like 75% of people traveling with children in their care. And this becomes important from an intervention perspective because it's a very different profile of movement. Whereas in Somalia, so for those of you familiar with the region, Bosaso and Garowe are key transit points along the eastern route, running from the Horn of Africa to the Arabian Peninsula. And so, this very strong pre-existing migration system of longer distance, irregular journeys towards the Gulf that involve moving overland towards coastal departure points along the Red Sea and then towards Yemen, really are reflected in the kind of movements that's taking place. And this, I think, challenged some of the more dominant thinking about climate mobility, which says that it's either more about immobility or short distance, because if there's a pre-existing migration system, then we do see these more internationalized migration outcomes. So I think one area where we could potentially see feeding into modeling is looking at how we disentangle climate disasters from other drivers of movement. And on the left, you see people talking about the interaction effects between their environmental hazard and other factors. So it directly threatened survival, it affected my living conditions, it related to other economic drivers, related to conflict at 22%. And then what I think is quite interesting is that 26% of people said, I could see that living in my place of origin would become too difficult. So people were even thinking about it in a proactive way. So they weren't necessarily experiencing that threshold yet, but they thought there's no improvement happening. It's only going to get worse. So I'm going to move in an anticipatory way. And then we asked people what the other drivers of their movement are like. And you can see the purple is Somalia, the blue is Kenya. So for Kenya, you see violence, insecurity, and conflict are a bit higher, whereas economic are higher for Somalia. So you see it's not a single driver, which we all know who've been working in the migration space for a long time, is really consistent with what we know about like the multiplicity of migration drivers in the process. And we ask people about the actual triggers of their movement. And here, I think the main takeaway also for time is that it's not one single trigger. Usually people experienced an average of 3, and they were typically loss of livestock, loss of crops, and increases in food prices that then yielded a migration outcome. And again, I think this also speaks to the timing of movement. So when do we see a more fundamental driver translate into an actual outcome? And the other thing that I think is important for modeling is looking at the diverse movement patterns linked to climate hazards. So I've already made the point about the migration systems, but we also see, which is not something I think we adequately program for on a humanitarian or development side, a single household exhibiting 3 different migration strategies. You see some engaging in these longer distance international movements, these like very much in line with the new economics of labor migration. It's a strategy to spread risk. you see much of the family engaging in shorter distance movements, and then some either choosing to be immobile or being involuntarily immobile. And that's the lower right graph. So not moving because they had to care for livestock, they had to care for land or keep their claim to the land, caring for other household members who were more vulnerable, being too old to move, etc. And here on the bottom left, you see the intended destinations. So most of those people that we interviewed who were from or who were in Somalia, they were migrants aiming for the Gulf, whereas in Kenya, they were looking at moving internally within Kenya. And then, I mean, Canada is really about a resettlement aspiration. I mean, that's where that links to. And in Somalia, you see people, this is the blue, they haven't reached the end of their journey. We've really caught them in transit. Whereas in Kenya, they have. Kenya is a destination in its own right. And the top is where you see the other household movements. We have information on the timing of movement, so how long people have persisted experiencing the hazard before it ultimately translated into moving. And of course, flooding, people were living in that for much later. It was much more of an acute hazard. Also determining the timing of movement. So we tried to insert a few more questions on our survey that could be more relevant to modeling. So what proportion of crops or animals did you leave before you decided to move? You know, what was the threshold? Which crops were the most affected and which livestock? Because I think in the field we see a lot of different types of livelihood programming taking place, and we want to see if these more drought-resistant crops or livestock, once they start to get affected, then do we see different movement outcomes. But it's mixed here because we also ask them, you know, before you decided to move, how did you change your current production? And we see some of the same things there. So this was definitely a challenge for us about how to be better at this, because we saw that the populations that we were targeting did attempt different adaptation strategies before they turn to migration. So 60% of households changed crops to adapt, 50% changed the type of livestock. And half of people received early warning systems information. So for anyone who's worked in Somalia, you know, we have the Somalia Disaster Management Agency, there's ICPAC for EGAD. I mean, there's quite a bit out there. You know, that people have access to. And then we asked, you know, what actions did you or your household undertake once you received that early warning information? And about 20% said they couldn't take any action because they lacked the resources to do anything about the information that they were receiving. But a lot of it was about selling assets. Okay, so I just want, before I close, and I'm at 13 and a half minutes, to say a little bit more broadly what the Danish Refugee Council does in the modeling space. So using more macro level data, probably the same that all of you use in the room. We have a few different types of models. I think some of the shortcomings that we've had is that we don't disaggregate well the type of displaced person. So distinguishing IDPs from refugees and asylum seekers. And that, I think that kind of precision is more what we need on the ground to look at how do we deploy mobile response teams. Whereas with our AHEAD project, it's been much better and the sort of the subsequent projects, but then, you know, it reduces the time horizon and the administrative level. So I think now what we're at the stage of is thinking, how do we take our micro level data and help make decisions? This is the data used for the modeling, and help make the decisions for the kinds of early actions that can subsequently take place, whether it's to deploy resources to help people not move if they don't want to move, et cetera. So any thoughts would be appreciated. And I'll stop it there.
Great non-modeling session. I wish that I could build my models on such great base data. Thank you for joining us. I think we got a time for just a couple questions before we move along. I've got one. Do you have a vision of existing models that this data might slot into? Is there specifically?
Yeah, so
That would be something I would love to discuss, because I don't know, given, given our sample of between 4,000 and 6,000, I mean, is that sufficient? Especially when you consider that it's across different countries. So when we drill it down to specific locations, is it a lot? Or is it more that we can use this micro level data to help us build better parameters or understand what to do once we have a prediction? But this is where we would love to work with people working on the academic side, because the reality is that our projects are 6 to 12 months. We're constantly filling the need for donors to get more data rather than to do sophisticated things with what we already have. And we rarely have the bandwidth to delve into this kind of thing.
Yeah. Some of the stuff that we looked at last session was based on damage, like single damage functions for all of Africa. So to me, like, 4,000 to 6,000 interviews, it seems like a wealth of data. So it's not my area. I don't know. Anybody specialize in migration in the audience?
it's all in a dashboard. So if anyone wants to use it or see the raw data to see how you can play with it for your own work, we will freely share it. So
Great. Thank you very much, Ayla. Oh, got a question here. Yep.
So I think I would be one of the users very happily using your data, which I think is extremely rich to inform modeling. That being said, what you do is extremely valuable. I think I'm thinking about what would you want to understand from the modeling side that could help your work? Or like, is there anything that we can give back so that you can do better work?
So many of the conclusions that we've drawn from the data are really from the descriptive level. For instance, the notion that it takes multiple triggers to yield a migration outcome, or looking at the timing of movement, but we haven't really tested it. So I think testing some of these assumptions that we've made, and I think also there's something really interesting to be done to look at, because we have perhaps a sufficiently large data set, to look at different climate hazards operating along different migration systems. Can we typologize what we're seeing and say for certain that that these dynamics exist, and hopefully help us build this out across different contexts?
Much. All right, next we've got Junkan Lee. And let's see. Going to be talking about voting with their feet, insights from storm impacts on internal migration in the U.S.
Not working.
Okay, hello. Good morning, everyone. Thank you for joining us. And this is a joint work with my colleagues from the. So Ian is a I'm an economist. Ian is an economist and environmental data scientist. Linda is my boss at Cornell. She is an engineer. And then the next two, Megan and Jamie, economist. And the last one, my former colleague is now currently in China, is an engineer. So it's a pretty interdisciplinary work. Well, today let's talk about the migrations and the nature disasters, how nature disaster induced migration, and since everyone here is working on those topics, I don't need to emphasize the importance of this. But I do want to emphasize is how poorly the current academia world was dancing. We are having a mixed result. That means that in understanding the general pattern for how the nature disaster induced the migration, which is largely unknown. And the one thing that the previous academic work still will mixed is they will somehow equalize the migration with the net population change. It's not necessarily true, but in my opinion, that migration is more like people's individual decision, while the population changes is actually the equilibrium result. And more importantly, we would like not only to understand the numbers, but also to understand the patterns behind how the people make the decisions and why they move and where they move to and who move. And that's why we have this empirical paper. We use a county level flow-based analysis to try to construct the large scales causal evidence for the migration patterns in the United States. And we focus on the hurricane disaster specifically, and that's why we focus on the 22 states in the United Coastal. And we're trying to find the patterns, so we're not focused on the single event. In total, we include 117 hurricanes from the 1996 to 2018. And we are glad that some of our previous studies that work on only one single event do find some similar results. So that means we are support each other. I'm a modeler, I'm a structuring guy, so I would like to use empirical work to speak to the structural modeling by providing some stylized empirical facts to tell them like how we should put some, or how should we revise the assumptions that in the previous model to better align with the what we find empirically. Also, we don't want simply do the number, we want to model and understand the decision makings behind. However, we cannot do like the survey data to directly ask the people why you're moving, where you're moving to, and therefore we use the public available data that use the observations where people come from, where people move to do analysis like the previous, the revealed preferences. And also we hope our models can provide some policy insights for the future. So what do? We use the IIS migration data as our key migration identifications, which is a flow data, county, origin county to destination county for each years. And we use a hurricane wind speed, which is the idea from environmental engineer, and we directly calculate estimate the wind speed as the identifications for the hazard exposure. And as exogenous, and since we have a continuous measure for the wind speed, so we can directly speak to the severity, not simple like the dummy, whether this places be affected or not affected. So in empirical strategy, we use the standard migration, gravity migration models plus our causal identifications framework to weigh fixed effect. And we do provide the placebo test by randomizing the shocks. And we also use the DID, which is a typical standard in the academia world. But if you want me to explain more about this, but later you can ask questions to somehow understand the mechanism. So what do we found? Okay, we found non-trivial, we would say modestly, non-trivial migration flows following the hurricanes. In total, if you only use the IIS data, we identified as 1.6 million more people that actually relocated across counties in the 20 years since 1999 to 2018. Since the IRS data will sometimes ignore the low incomes that will not require the tax filing. When you adjust these, use the ACS survey-based migration flows, then this number reached to 2.2 million. Whether this number is big and small, you can decide, but I would say typically, definitely non-trivial. And in terms of the flight composition, we found some flows from the NIC means non-impacted counties, DIC means impact counties. Flows from the non-impacted county to the impacted counties increase with a small number. There's a substantial out-migration from impacted county to the non-impacted county. That means out-migrations from the risk area. And there's also a large number of people who relocate but still stay in the impacted county. So it's about 50%. Our results indicate that household in the United States do trade off the economic opportunities during the recovery and the risks of the hurricanes. But the risk perceptions was different. The one who has impacted by the hurricane will value the risk more than the people that haven't been impacted by the hurricane. And the weight is different, and that's why they behave differently. So the one that think hurricane is important, even though they see the economic opportunity, they still choose to move out. But the one who hasn't experienced, then they will weight the economic opportunity more than the risk, and then they try to move in. And this migration response was vary over time, and it varies with different income groups. However, I'm not sure if I have enough time to dig deeper inside. If I don't have time, please make sure you ask a question about that. Okay, so Siri. Let me make it short. So we're starting from a standard residential sorting theory that's widely used in academic words to describe where people choose the locations. And I only made one revision is that I added something that how people according the happenings in the hurricanes in this region and decided their preference to these locations. And with some mass, so our migrations flows can be decomposed in two parts. One is standard gravity component, which including the pull and push factors that depend on the origin, destinations, characteristics, including the economics ones, the populations, and also the distance, the migration cost. And another the one that's directly related to how you evaluate the natural disaster. One thing that really pissed me off is in the previous literature, the general assumptions for this type of model is people evaluate the happiness of the hurricanes identically. That means that everyone, whether they has been experienced or not, they will have the same assumption. They will think the preference to a place that has the hurricane. And in this case, yes, migration equals the population, net population change. Because if the hurricane is a good places, then everyone want, if a hurricane is a good thing, then everyone want to move this. If a hurricane is a bad thing, everyone want to leave. And therefore, based on this observation, then we can use a very simple way to identify our, to identify this, or to verify this assumption. Sorry. To verify this assumption by just looking at the two places, one is being affected by the hurricane, one is not being affected by the hurricane. If the flow from the affected to non-affected and from the affected to the non-affected to the affected has the opposite direction response towards the hurricane, then that means the assumption may be true. Otherwise, there may be something that hidden that we haven't discovered. Okay, risk design data. So IIS data for the migration and the hurricane exposures from the Anderson's paper that we use a 1 minute sustainable maximum wind speed, which is the standard in the hurricane literatures. And we construct our data from the event because some hurricanes will happen in the same year to the anti-year and match with the annual migration flows. And this is just a picture show the over these 20 years how the hurricanes was spatial distribution and how the hurricane track is, just showing how risky we are, and the randomization assigned according to the nature that's validates exogenous and randomness of our treatment. And we also included the other controls, economic controls, like the wage, unemployment rate, housing price, and also the travel distance as it goes. Now the identification here. So carefully thinking about this, we have previously studied in the hurricane literatures identify which county has been affected, which county is not affected. And in this case, we use the wind speed as a measure. So we consider the 1 minute sustainable wind exceed for 19.5 meters per second as the threshold in the baseline. If the hurricanes happens and the wind speed past the population center of the county, over that threshold, we think that's a treated county. Otherwise, we think this county was not affected. And this is one dimension. However, we're studying the flow. Each flow has two nodes. Then this means we have considered the origin and the destination at the same times. So we have 4 cases now. The origins impact, destination not. Destination impact, origin not. Origin and destination both impacted, and origin is not impacted. A natural choice for the control groups is the counties that origin and destination are not impacted. And the origin, and then the other 3 types, since we don't have any pre-assumptions about the functional form of those 3 types the treatment. So we have to consider 3 types modeling together and use 3 separate functions to capture these 3 types of. The type 1 and type 2 are the ones. Type 1 and type 2 are the ones that we are focusing on for our empirical test. And then for the type 3, we will use the various types of the assumption to catch that, and we will talk about this later. Okay, the model. We use the gravity migration models, and we use a 2-step because the data available for the migration data and for the hazard data, they don't match. So for the migration model, we use all the migration observation that were available and construct the simple standard means migration model controlling for the population economic choices, and then we calculate the excess migration. The excess migration, then we relate these excess migrations with our hurricane exposure variable to test whether those hurricane will impact the flows, migration flows, and this were found. So first set of results showing that the standard migration models controlling for the population and the economic characteristic of origin destination. So we found that population has a both positive side, and we do find that the poor factors that from the destination, that the people move to the high wage places, people move to long-employment places, people move to the place with higher job growth, people move to the places with the higher with a lower housing price growth, and also because there are some worries about the IRS data after 2011 due to some technical changes. Alex still writing emails sending me to addressing these concerns. So if you meet Alex, please send him my appreciate, really appreciate it, like he pushed me towards to that ends. And we have found that using the data prior to the 2011, we do find a similar result. So in these terms, those results, we get consistent from the 2 sets of. And then the second is our key result for the migration. So the first column, where we only use the dummy, which means just identify whether this flow is from the impacted regions to non-impact region, and this flow from non-impact region to the impacted region. That's directly addressing the average treatment effect. We found positive for all. That means more people moving from the impacted area to non-impact area, and at the same time, people moving from non-impact area to impacted area. And then the second column, we use a baseline. We use the baseline model, including the continuous wind speed measures, and also including log of the distance to characterize the effect of the distance on these. So we found a positive side on the wind speed and the negative side on distance for both. That means the migration patterns, the mutual migration patterns are very similar. People moving to the more severe apparent impact effect, and the people from the more severely impact areas also move out, and this was decayed by the distance. That means the migration costs really matter. And the third column is a relative migration, which is the result that more directly related to a theory. But since relative migration is not like a straightforward explanation of the migration itself, so we show this as a robustness check. Then we also do the test for the number for the data as prior to 2011, and we still found it similar. And then we focus on the more like hurricane-prone areas, including the 8 states in the Gulf and the Southeast. That's Texas, Louisiana, Mississippi, Alabama, Florida, Georgia, South and North Carolina, and also then focus more on the Gulf Coast region. We all found a similar result. So our result is robust.
Well, we've got 5. I miscalculated. It's 18 minutes apiece. Okay, then let's. We do a bunch of robustness tests to make sure that our result is sure, and doing the mechanism check. And our mechanism is really as what we introduced in the introductions, that people trade off between the economic opportunities and the risk, and the risk perception was different, and that's why we see the different breadth. And finally, let's show like only two pictures about the quantification. So first, since we can model the migration, so we put all the migration, the number estimated, the number of the people migration due to the hurricane, together, and the shared area is the most devastating hurricanes in the United States. First, they are very aligned with each other, and second, we see a quick response in the short run, but somehow decaying in the long term, which indicate that hurricane has an impact that will concentrate the migrations over time, just following the 1 year, 2 years after the hurricanes. And then especially we calculate the out migration from the impact area and the in-migration period. These two pictures are very, very similar. The out migration and the in-migration happen same times in the same way. And that's why when you see the spatial distribution of the net population change, you get mixed results. And if you look at it spatially, there's loss and gains in the population, and who actually gain the population just as those big cities nearby the impact area. So that's our finding. Yeah. I'm sorry. That's a good modeler. I based my my modeling for this session on the last session, but we only have 18 minutes apiece, and that's even no time for questions. So I apologize. A little more cramped this session. Jonas, Haas, why don't you come on up? Modeling coastal futures, event-triggered adaptation decisions for protection or retreat in a stochastic framework.
Thank you. Hi, everyone. My name is Jonas Haas. I work for the Global Climate Forum in Berlin, and I'm going to introduce to you some ongoing work I'm doing for my PhD. This work is funded by 2 EU Horizon research projects, namely the Decipher project and the ACREO project that work on climate change adaptation. I'm going to talk about how to model coastal futures, and specifically about a model that we are working on, which is the event-triggered adaptation decision model for protection or retreat in a stochastic framework. Sorry, it's not working. Yeah.
Try it again.
Yeah, thank you. So why is this important? Flood risk modeling shows that already today, globally, around 35 million people will be flooded annually, causing expected annual damages of roughly 307 billion. Just to get an idea, Hurricane Katrina caused around $125 billion damages due to the failure of the levee system in New Orleans. Also, similarly, the Hurricane Sandy caused devastation across the Atlantic. These numbers are bound to rise due to the sea level rise projections that are projected to rise by up to 1.1 meters by the end of the century, according to the IPCC. Furthermore, this is also exacerbated by the socioeconomic development. So you have migration going to the coast rather than away, which will expose more people in the future to coastal flooding. Today we have around 900 million people living in low elevation coastal zones, but this number will increase by 100 million to over 1 billion per people living in coastal zones by 2050. Despite that, we can observe that adaptation interventions that are necessary and would be cost optimal or cost benefit optimal are stalling. And we see that in the real world, adaptation often happens reactively. So especially retreat as well happens often as a consequence of large disasters that destroy a large fraction of the capital stock of the housing stock. For example, in Holland and in England, we had the Great North Sea Flood in 1953, which caused massive destruction and triggered the Delta Worken project in Holland and the famous search barrier construction in London. Similarly, in New Orleans, Hurricane Katrina triggered the Hurricane and Storm Damage Risk Reduction System, which is a combination of storm surge barriers, levees, and other measures to prevent the reoccurrence of a similar event. But we know that today these risk reduction measures are already not sufficient anymore. And there are many other examples like the North Sea flood in '62 in Germany. So we've pursued two objectives with this research. The first one is to develop a framework that more accurately represents the adaptations dynamics on coasts based on the event-triggered adaptation model. And secondly, we want to advance the large-scale flood risk modeling by moving beyond what we call the expected annual damages approach and integrating stochastic extreme events into the assessment of adaptation. So expected annual damages we can basically define as the integration of the damages over their probability of occurrence. So they represent the average yearly damages of flooding by combining the magnitude of the events and the frequency by which events happens. There are some advantages to this methodology. For example, it's a relatively easy to use risk indicator because you can calculate it and then compare it to, for example, adaptation costs in the future. Use it straightforward in cost-benefit analysis. And it's also computationally frugal enough to use in the large-scale assessment, global assessment, for example. On the right side, you can see two studies that employed this methodology. For example, Hinkel and colleagues and Diaz and colleagues. And as you can see already in these images, the expected annual damages are increasing smoothly into the future, which is not a realistic assumption of how damage will actually work out over the course of the century. But this is the disadvantage of using this average flood event per year assumption. In terms of adaptation, this assumes then that we have a rational coastal planner that has perfect foresight, that implements at the beginning of our model runs the optimal adaptation measures. And it disregards social barriers to adaptation that we can observe, which might stall the implementation of necessary adaptation actions. So also if you think in terms of economic modeling, for example, what we usually do is we deliver these expected annual damages that we project into the future to economic modelers, macroeconomic modelers, that then use them as economic shocks. But we pose the question whether this is actually a good approximation for economic shocks that normally don't happen smoothly increasing in the future, but they might happen. There might be a large shock somewhere in 2030, but then there will be no shocks for many years. And we also disregard, using this methodology, the high-end damage events that might overwhelm the economic, the capacity of the economic system to adjust. So in this image, you can see a very simple, basically representation of what we are doing. Basically, we draw a flood event for a coastal plain. We calculate how much damage does this flood event cause. And if a certain threshold is exceeded, then an adaptation action is triggered. And at the moment we implement two different adaptation options. We have either the option to abandon the damaged assets and retreat the people to higher ground and rebuild, or we can reconstruct the damaged assets if the damage was not high enough and build protection. Of course, it can also happen that none of those two options is optimal, and in that case, there would only be reconstruction happening, but no actual adaptation. The damage threshold we are using is derived from a concept of nuisance flooding by Moftakari and colleagues. Basically, they found that flooding events that are less than 10 centimeters, they don't cause any significant amount of damages and only minor disturbances to everyday life. And what we did is we took this 10 centimeters and calculated using a depth damage function the fraction of assets that would be damaged in our model, and we came to the conclusion that it would be 9% of asset value that is destroyed by a flooding event. But yeah, we're happy to discuss this as well and maybe find better thresholds. To explain a bit the model process, I created this image. On the left side, you can see the Monte Carlo framework in which we implement the model. Basically, we start by drawing a random extreme event for coastal floodplain, which we then apply and calculate the damages that are incurred. So if these damages then pass a certain threshold, the adaptation action is triggered. Lastly, we store the results. So we store the damages and we store the decision outcome and start the loop over for all time steps in all floodplains. On the right-hand side, you see a flowchart of a really simplified version of how the adaptation decision works. Basically, what we do is we employ a cost-benefit analysis. We minimize the total flood cost, considering all future damages as expected annual damages, but we're also considering the reconstruction costs that would be incurred today or at the moment of a major flood, and of course also the adaptation costs today and in the future. And the outcome of this optimization will then be either to reconstruct and implement protection measures, to reconstruct but not implement any further adaptation, or to abandon the assets and perform a retreat. We implement this in the Diva Coast Julia library. If you want to check it out, you can click on you can scan the QR code and check out the GitHub. Basically, what you see in the left picture is a representation of the floodplains in our model. The purple areas are the floodplains. So what we do is we perform the whole Monte Carlo simulation and the adaptation decision model on each of those floodplains. This is the North Sea, but we have this available globally. And globally, we have more than 150,000 floodplains. And we can so far model it up to 2100 or even further into the future. So the next steps are the actual coding of the framework and the adaptation model into the Julia library. We are also still thinking about how to improve the retreat component of the model because we don't consider, for example, return migration. Basically, what we do is we just remove these people from the floodplains. Also, we are working on an implementation of spatial dependence of floods to better represent or to more realistically represent the flood extent. So to conclude briefly, the event-based adaptation model more accurately reflects the real-world decision-making in coastal floodplains. We explicitly account for flood damages and reconstruction, which is not done in the expected annual damages approach. And we improve the representation of extreme events by drawing from an extreme value distribution, basically. And we explicitly account for the uncertainties in the extreme water levels through our Monte Carlo framework. Thank you very much, and looking forward to some questions.
Following our paradigm of rewarding those who are punctual, why don't we have a question?
I was curious if you Nicole, Integral Consulting, environmental consulting firm out of Seattle. I was curious if you allowed the risk perception piece to be folded back into the random draws, or if you allowed the random draws to impact the risk perception rather. So in your, I don't know if it would help if you went back to your model, but.
Yeah. So which slide are you referring to?
The visual display of your Monte Carlo model. Yeah, so the idea being that people's expected future damages changes if they have a really, really bad event, as opposed to having like a nuisance flood. They think, well, okay, if this happens again, it's probably fine. Maybe it won't happen again. Versus if you have a horrible thing happen, like, okay, let's, their expected future damages, their perception changes depending on this random draw of an event.
Sure. No, so far we don't consider that, but I think it would be a really valuable extension. We are also still thinking about how to frame this threshold. So because now, I mean, it makes sense, but it's maybe there are better ways to represent that. Because of course, a decision is there might be a different decision taken if the event causes 50% destruction to the assets, or whether it's 9% or 10%. So it's not, we are still thinking about this, and we are welcome to any suggestions that people might have as well.
Thank you. But I also have some similar questions for your model, like your decision rules. So who are actually making that decision? Because for the individual levels, like you construct the protections will unlikely happens, but if you're at the government level, then government may consider the wider, broader, like economic benefits for protections versus the losses and the chaos after and the losing population, or those things. And if you're assuming they are like perfect foresight for the futures, or they are basically on like a rational expectation, or those things that in their mind, or there's any like or maybe you haven't like adjustment for the tail event, the like the 1 in like 1,000-year flood that possibly happen.
So basically, we do assume that the adaptation decision, if it is triggered, is then taken by the coastal planner. So it would not be a household adaptation, but it would be the coastal planner that optimizes after the event, and then implements policies to allow her to manage the adaptation. Does that answer your question?
All right. We have Madeline Kitch here. Oh, there she is. Okay.
Thank you.
From Carnegie Mellon, she will be speaking on a theory-grounded computational framework to quantify social and environmental justice concerns for technical decision-making.
Hello, I'm Madeline. I am an incoming PhD student at Carnegie Mellon, and I study computer science. And this is some work I've done over the past year at MIT with Bailey Flanagan, who is a professor of computer and political science, and Alec Westover, who does work on like AI security. And so the name is slightly different.
Madeline, if you could speak.
Oh, okay. And so the name of the presentation is a little bit different than the abstract, but I think more captures what I'll be talking about today. And so it's a computation-aided approach for facilitating community input on environmental justice mapping tools. And so I wanted to start with what my definition that I use for environmental justice is. Environmental justice is a meaningful involvement and fair treatment of people in the creation and implementation of environmental policy. My work works on the meaningful involvement side, and it says, for questions of really technical decision-making, how do we actually involve affected communities in these contexts? And so I think there's been a lot of examples already today on different indices, measuring natural hazards, mobility, and habitability. And so how do we like involve communities and what these should look like? Concretely, the project that I've been working on started about this time last year in Pasadena, California. I was at a planning commission meeting, and one of the planners was presenting on what they had started for their environmental justice element. And she was basically asking the question, we have this state-level tool called CalEnviroScreen that identifies what they think are the disadvantaged communities in this city. Are these really the disadvantaged communities in the cities? Have we actually captured all of the local contextual components that people care about? In another way, she was saying, we have a map made by the government of these communities. What would the community make? And so I started thinking a lot about this question. And California is not the only state to have these mapping tools. So here's one from New Jersey called EJMap, Michigan, Colorado, and Maryland. And they're used for grant allocations, they're used for permitting decisions, they're used for planning requirements. So these are really important. And really the second thing to note about these tools, which makes me very happy, is that they're functions. So I have right here like basically a linear function. They're not quite linear, and I'm happy to talk after about why this is okay to make for right now. And generally they have two components. They have an environmental burden component that looks at different risks and aggregate those risks. And they have like a social vulnerability or political burden component that kind of says like, given those environmental risks, like how do other social and political factors compound those risks? And these create this overall score. And because we care about community input, one question we might want to ask is how do we get community input on a function? Let's ignore the function part. What about just community input? So we could vote, and maybe people would have a ballot that looked like this. If I was a voter, I would be like, what do these mean? Like, I have no idea what to decide here. And furthermore, there are 3 functions here, and actually there are infinitely many functions we could consider. So I'm going to say this is not a good approach. Another idea is we could have like a town meeting and like people can talk about like, what are some things that you experience? And then the people in government could say, okay, I get what you're saying. Like you're actually saying that this should be the score function. I would also say it's pretty unclear how to make that decision. So maybe we need another method. And this is where the computer science comes in. So just like to briefly say there's a lot of things that you could want to input on. You might want to ask, like, what are local indicators that people care about? Another question you could ask is like, which ones are more or less important? We are going to focus on the importance part for now. I could also think about the local indicators in the future. And the goal is to learn these weights corresponding to fire risk, extreme heat, and air pollution. Okay, so previously we were basically asking some type of question of the form, what should the function be? People were voting on a list of function candidates. The question we probably actually want to ask is, how should it behave? And so here's like an example of a question you could ask. And there are actually a lot of different questions that have basically the exact same mathematical properties. So if this one doesn't look good for your context, I'm happy to talk after about ones that would work. And so we're basically saying, okay, there's this community that scores pretty normally on fire risk and extreme heat, but has a pretty high level of air pollution. How would you say like the environmental burden is for this community? And people would place this community somewhere on this line, and we can infer from their response what their weight is on fire risk. And this question popped up immediately, but what about like their weight on heat and air pollution? Okay, so this reveals another thing. We can't just ask one question. So let's ask more questions. And as you can see on this slide, I've asked 3 questions, but I've actually learned no more information. And really the problem here is that we're only changing the score on one variable or one indicator. And in order to learn a lot of information, you have to ask about different communities. From a mathematical perspective, this relates to ideas of linear independence or orthogonality. So basically, we need a more principled approach. Okay, yeah, how do we choose the communities? Okay, and this is where, so like computer science really comes in. We have some type of learning algorithm that says these are the set of indicators we care about and a bunch of other parameters you might want to specify. They give people a list of communities to evaluate. And then from that, we can output this scoring function that represents their beliefs as inferred from their evaluations. And in particular, things that we can answer is, how many questions do we need people to ask about? Maybe this approach would be practical if we ask like somewhere on the order of like 1 to 10 questions. But if we're asking people 1,000 questions, nobody has time to do that. And then how does this number depend on how close we want to get to people's beliefs, how consistently people respond, do they have the same weights for every question, or are there like differences, and also how many indicators we want to ask about. I have answered all of these questions theoretically, so if you guys are curious, happy to talk after. Okay, but there are a lot of other considerations you might want to think about. And so one of them is, what are the indicators we actually want to ask about? These tools can have anywhere from like 3 to like 50 indicators. And so because the number of questions like scales with the number of indicators, that is maybe not the best thing to do. And also some of the indicators are like slightly not interpretable. It's like, what is the concentration of PM 2.5 or like ozone? But really people might just care about like air pollution. So I think that is like an important question to consider. What is the question format that is most understandable to people? So I presented this idea where people give like an environmental burden score, but they could also compare like some hypothetical community to their own community in terms of like environmental risk, or to an average community in a political district. There are a lot of options. And I think the last one that I think is especially interesting is everyone is going to have different weights. They're going to have different beliefs. And how do we still create a mapping tool that reflects as best as possible what people care about and reflects ideally a diversity of preferences? These are all like very interesting questions. And then the last one in particular relates to an entire branch of computer science called social choice theory. And so to close, I want to kind of leave with you guys with some questions. This is an idea. And so I think it's important to see like where this fits in the context of policy making and decision making. how could a computational approach like this be helpful? What are some potential unintended consequences of using this type of methodology? And lastly, what are additional considerations we need to make in order for this to be as practical and equitable as possible? I've thought a lot about all of these questions, but honestly, I think the most important thing would be to get your guys' input on what these answers would look like. And so to close, I have a short survey. If you guys are able to answer it, it is completely anonymous and it will only like guide kind of like how I think about this, how I write it up, and then additional things I can think about in the future. And then I also put my email in case you guys are interested in kind of using community input and sort of like risk assessment and basically technical modeling. I'm happy to talk.
All right, that got us back on time. We can take a couple more questions perhaps while Kelly's getting set up. We get set up for Kelly, sorry.
I have a comment.
Okay.
So I'm from Alaska, and we looked at the 144 most threatened communities there from erosion, flooding, and permafrost degradation. I'll give you a link to that. But it's many years to look at all sorts of different threats, and then how do you combine the threats, time to damage. So it doesn't take don't have time to ask all the communities those questions, but I think it's one example of a pretty well done analysis that maybe would be relevant.
Okay, super cool. Yeah. Yeah, and I think there's also like other methodologies that could kind of circumvent the problem of like you can't ask everyone all the questions. Like you could ask everyone a subset and then aggregate those directly. But yeah, I would definitely be interested.
Okay.
So thank you. I come from an economics background, and
Okay,
I'm sure you are also thinking a very similar thing. We think all the time about trade-offs and how we measure those trade-offs, and there's revealed preference and stated preference, and you can deal a lot, between those, and survey methodology is one of the ways in which we do that. I'm curious where the data science portion fits in, because from my perspective, I'm thinking with, well, can you create a survey that just asks people a couple questions and then it's revealed preference? You can actually come up with those weights based off of what you put in those questions very strategically. And you can explicitly ask people, how much would you pay for this thing? How much would you pay for that? But you can be really intentional and have those preferences revealed to you. And so I'm curious, was your work mostly around the more of the technicalities of like how many questions do we ask in order to get the answers that we want, and like more of that kind of math stuff? Or was it more of like, how do I design a survey to reveal weights?
I would say so. Like so far, most of my work has been on the first question, but I'm actually really interested in the second question. Yeah, and actually, so there's an additional motivation for this work, which came out of my thesis last year. And one thing I found like kind of unconvincing in economics is we have these things called welfare weights. And I think no one has any idea what those should be. And so like kind of another use case of this would be able to like actually calibrate these models with weights that reflect what people care about. Yeah, but yeah, very happy to talk.
Thank you.
Any other questions from the audience before we move on? Okay, Kelly, why don't you introduce yourself?
Hi, thanks everybody for your attention today. This is the last session before lunch, so hang in there. I'll try to keep it short. All right, anything's going on. All right, so today I'm going to be introducing two tools for assessing, communicating, and responding to sea level rise and coastal flood risk. So these where these fit into the rest of the presentations are looking ahead to the climate impacts that we're going to have in the future, and hopefully more effectively communicating them to people who might want to be making adaptation decisions, aspirationally before these disasters hit, and they're responding, to their home being flooded or something like that. So Before I get into the tools, I'll just tell you a little bit about where I'm coming from. I'm work at Climate Central. We're a nonprofit that's nonpartisan, non-advocacy, 501c3. And we're basically scientists and communicators who are trying to take climate science and localize it, make it understandable, and get it into the hands of people who can speak to communities about it. Um, We've been making sea level rise and coastal flooding tools as well as other climate impact tools for over a decade, and they've been used by millions of people. When people download fact sheets or graphics or whatever from our tools, we give them the option to tell us what they're going to use them for. And so this word cloud shows the most common words that they type in when they're downloading stuff from our tools. So we find basically that people are using them for a lot of research, but also for communication, education, and that sort of thing. So now that you've gotten that primer, the first tool I would like to share with you today is Coastal Risk Finder. So this is an interactive web tool for exploring sea level rise and coastal flood projections, impacts, and solutions. So we have data that is downloadable at CSV format as well as graphics. You can customize what year, pollution scenario, and flood level you're looking at, and we localize all the information to the state, county, municipality, congressional district, state legislative district, and I'm probably missing some geographies there, but we really try to break it way down. And before I demo the tool for you, I just want to share kind of like the science behind it. So the way we do these analysis is we start with land elevation data from NOAA. We refine that data using levee data from the Army Corps of Engineers. Then we stack on top of that elevation data sea level rise projections. We include ones both from the IPCC and from the National Oceanic and Atmospheric Agency, or actually, sorry, the U.S. Interagency Task Force. Whenever I say that, NOAA always wants me to give credit to the other agencies as well. And then we stack on top of that coastal flood projections. We include both, we include the annual flood, 10-year flood, and 100-year flood. And I'll just note that this is a bathtub model, so it's not as sophisticated as some hydrodynamic models that you may have seen for a smaller location, but we're trying basically to provide a screening level tool that provides dozens of different scenarios. In this case for the US only, but we also have maps that are global. So the keeping it screening level allows us to have show a lot of different scenarios for a really large area. And that kind of comes as like a step one, hopefully helping people who want to do, more expensive and sophisticated modeling, an idea of where to do that modeling, maybe advocate to get funding, communicate about it, kind of like as a first step. But anyway, once we have, we know where we expect the flooding to be, we try to figure out what's impacted. And the first step in that is looking at building footprint data from Microsoft. So they've used satellite imagery to identify buildings. And so we basically are seeing which of those buildings, the structures, are going to be in the flood zone. And then we assume that housing units and populations are equally distributed amongst those buildings. So this provides a slightly more sophisticated modeling than just assuming that people are equally spread in, say, a census block or whatnot. Because a lot of in rural areas, especially with lots of wetlands, that can kind of skew the data. Yeah, so you can use this to aggregate and look at a certain slice of the data. So if we focus in on a 100-year flood in 2050, you can aggregate that all together. This is for the contiguous United States. There are 2.5 million people living in 1.4 million homes that are in that 100-year floodplain in 2050. So pretty staggering numbers. We also have this data broken up by different demographics. And one that I'll highlight is that people over the age of 65 are disproportionately at risk. They make up 22% of the at-risk population, but they're only 16% of the population in those coastal states. We also can break down this risk by geography, and unsurprisingly, Florida has the most people at risk, but maybe a little more surprisingly, the really densely populated coasts of New York and New Jersey come second. But what's really, I think, the most value of the tool is being able to go down and zoom in to really specific areas when someone's making a management decision. And that's where the tool comes in. So this is Coastal Risk Finder. I'm going to attempt to demo it for you today. Oops. Maybe. Okay. I'll switch over and see if this will work for me. Okay, here we go. A little bigger, perhaps. Nope. Well, sorry. Get it out from under the. That works. All right. Thanks for your patience, everyone. All right. So this is the tool. I want to show you how it works, and I invite you to follow along on your phones if you prefer learning by exploring to actually listening to me talk, which is fair. So you can access the tool at app.climatecentral.org/coastal risk finder. And that'll bring you to this page here where you can search for any coastal location. Like I mentioned, we have data for states, counties, municipalities, congressional districts, state legislative districts. And just before I show you the tool, I also want to highlight that we have these user guides on how different folks what different folks might find most useful in the tool and how to use those features. So I'll go ahead and search for a location. Let's do New York City because that's where we are. Cities. And that'll bring me to this page here where we see basically with settings on the left here, map in the middle, facts on the right. So taking those one at a time. This title up here tells me what I'm looking at. By default, the tool will go to an annual flood in 2050, but you can choose to change the scenario, look at a different year or a different flood level, look at sea level rise alone or a higher flood, as well as change what pollution pathway you're looking at. Once you're done with that, you can roll all of this stuff up and explore the map. This is kind of like, it's built on Google Maps, so hopefully it's very familiar to folks and easy to navigate. And lastly, like this is where the real data comes into the tool. On the left side, right side here, I don't know my lefts and rights apparently. You have these data cards where we have, there we go. We have impacts, projections, and solutions. So we can see how many people are at risk in this particular scenario. And if I click on any of these cards, it'll bring me to a page with more detailed data about that, including a data visualization that, and I can download this data as a CSV or the visualization as a PNG. We also have information down here about the methodology and the data sources if you're interested. Similarly, for projections, we can see graphs of expected coastal flooding or of different flood levels over time, and to download this as an image as well. And finally, we have information on solutions. So we have both kind of generic information on how to adapt to flooding as an individual, steps you might take, linking to a lot of government sources, the Red Cross, other groups like that have done a lot of work on this, as well as briefs on adaptation in each state. So this includes basic information about if there's a plan, what government bodies work on this stuff, example projects, and resources. Yeah, so that's about that for, now I'm gonna struggle to get back to the thing. PowerPoint. It's not in PowerPoint, it's in the, oh, I see. Got it. All right, I'm learning. So that's that tool. I invite you to check it out. And next, the next tool I want to share with you, this one's a little more innovative and exciting, perhaps. This is our Flood Vision Risk Viewer. And this is a library of photorealistic street level visualizations of projected flooding. So what is Flood Vision, you may ask? It is, we call it basically Google Street View for flooding. So we have a car that or a couple of cars that we've affectionately named the Flood Rovers that have a variety of sensors on top of them. We can basically drive down the street and collect stereoscopic imagery, LiDAR data, very high quality GPS data, and that allows us to build a 3D model of the space that we've driven through. And then we can use AI to render in a flood level on top of that very precisely and based on whatever scientific projections we want to use. We have like NOAA and IPCC models built in, but we've done work with like Delaware and Florida where they have their own models and then have added those. So we also can extract from those 3D models entry floor elevation measurements and other like elevation measurements in a building that can be useful for like the National Flood Insurance Program or FEMA regulations and stuff like that. But basically, we think these images can be really useful for people to start these conversations about what risk is coming, to think about retreat and or other adaptation options and kind of make it concrete. So this is a evacuation route in Florida. And this is, well, this is an evacuation route in Florida. And this is what that evacuation route might look like in 2050, experiencing the 100-year flood. And this is what it might look like in 2070 with that same flood level. We can also show homes. This is in, I believe, Ocean County, New Jersey. And this is the same home experiencing a 4-foot storm surge. Sometimes people always react to the like iconic locations. So this is Nathan's famous hot dogs on Coney Island. I don't know how many of you are from New York, so this might not land as well as I had hoped, but this is the same location experiencing again that 100-year flood in 2050. Yeah, we do blur the people's faces and try to not use the ones with lots of people being in the floods, but it wasn't really possible to get one of Nathan's without people in it. Anyway. And then, yeah, there's also, we can look at critical facilities like this EMS station in Monmouth County, New Jersey, showing the same thing in 2050 with a 1% annual chance flood. So you can access a library of these existing visualizations in our risk viewer. So this is at climatecentral.org/tools/floodvision-risk viewer. And basically, we have visualizations collected here from a tour we did driving from Maine down to Texas along like the coasts of America, the East and Gulf coasts of America. We have a lot of sample images in there, but we also have a lot more data that we can use to render more images. So if you're interested in images of a specific location, feel free to send me an email. You can get my contact information and links to all the tools here. If you're interested in any specific thing, please feel free to reach out. Please feel free to reach out if you just want a demo of the tools or have questions about how to use them as well. So, thanks for your time.
Well, can you go back to the emergency management flood?
This one?
So, I mean, one of the things I challenged the first group to think about is that all models are wrong, but some models are useful, right? So if I worked here, I might say, all right, we're okay. You know, we might have a hard time getting out, but we should be able to adjust, and our emergency management district is okay, right? But as you know, these models are highly uncertain, right? And the communication of sort of a hyper-realistic view of what might happen based on data that's highly uncertain may lead people to make conclusions that that aren't efficient, that aren't useful. They're counter-useful, in fact. And if you, for example, if you go back to your slide on what would happen at 250, or what was it, a 100-year event at 250? No, annual event at 250, right?
I don't remember.
What the exposure might be to the population.
Oh, yeah.
Yeah, I would challenge you that that's probably you're off by 100% here, right? Because if this is the annual year in 2050, then there's going to have been an annual flood in 2049, 2048. There's going to be 10% likelihood in any given year. And in fact, most of this exposure actually won't be here in 2050 if that's based on the annual flood. So I think we have to be very careful when we come up with tools that are based on, you know, hyper-realistic AI to try to communicate risk, that we make sure that there's sort of a scientific basis for that risk, and that we're really focused on the decisions that are trying to be made, and make sure that they're made appropriately. I wonder how you'd respond to that.
Yeah, I mean, I think that both the facts and the images are showing what happens if we don't adapt. So the idea of most of the flood vision work that we've done is in partnership with like Sea Grant or local communities that are trying to do this adaptation work. And so we're trying to present a world that we hope doesn't come to pass. We're showing people risk before it happens in the hopes that we will mitigate that risk. It's certainly true that there's like, yeah, all the modeling is not not going to match up with reality 100%. But I still think that there's value in showing people what our best estimation of what that risk will be if action isn't taken.
Any other questions for Kelly?
You can a scenario for sea level rising or combine with that. So to get the
I'm sorry, Junkan, you're hard to hear here.
That's right. This.
I was thinking EU data is good because you have the elevation, you have flood depths, you have directly visualizations of how bad of the sea. But in the research purpose, I was curious about the two things. Whether one is like whether you data can really transfer to some economic losses in terms of building losses. That's one thing. The other thing is we would like to see the functionality of the local buildings.
Yeah, I mean, we would love to add like loss damage functions to the exposure analysis. This is the first release of the tool, and we hope to basically add more information about what exists in the floodplains. So probably next we'll be looking at critical facilities or schools, TBD on which one. And then property value and stuff like that is certainly in the roadmap, funding willing, and all of that. But yeah.
Okay, I think we're at time. Thanks, everybody, for being punctual and a great session. Let's give a hand of applause to the presenters.